Large eddy simulation, or LES, is basically a turbulent model that's also well known. And some researchers says that this model is like a future of turbulent models because a lot of important flow details cannot resolve by runs. But the main problem now with the large eddy simulation is the computational effort is still higher than the runs. And let's go discuss a little bit about this turbulent model. So the fluid flow basically has like if we have a complex flow and consisting of a swirling motion, or called the eddy. Along the way the eddy is moving, it dissipates or like transforms into some smaller eddies or smaller diameter eddies, which has different energy. So it's like a dissipating energy in the form of the smaller eddies, and over time it will also become smaller and smaller until it reaches the smallest scale, known as the Kolmogorov scale. And after the eddy has become that small, or become that Kolmogorov scale, the viscous force, or the viscosity will be dominating the flow or dominating the eddy, that makes the eddy become dissipated as a heat. So it will be like simply gone. And by using this idea, we can construct our filter to the simulation, or to our model, to simulate some specified value or some specified diameter of eddies. With this kind of filters also known as the large eddy simulation. So we can easily capture the eddy of this flow. And this is the turbulent energy cascade that we can imagine, or we can view that in the right direction shows that the wave number, or the inverse of the eddy diameter, is larger, means that the diameter will be smaller in the right direction. So if we have large eddy or large eddy diameter, we will have large kinetic energy density, and as the eddy goes smaller, the kinetic energy density become also smaller. And this curve is often found in the experiment. And so the smaller the eddy, the smaller also the kinetic energy. So sometimes we have not to fully resolve the eddy, maybe like 80%, to get the most of the flow features, let's say. So the mesh will not have that small to capture like 80% of the flow features. So it is an important insight, because most of the kinetic energy density consists in the large eddy flow. But again, by not resolving the smaller eddy or smallest eddy, we cannot you cannot see the detail of the flow nearby the walls, which again is one of the drawback of the large eddy simulation. And the idea here is to make the mesh as small as possible, so we can capture the motion of the eddy. So basically, by using this large eddy, if we have that, let's say 4x4 mesh, we can easily capture the detailed motion. And the smallest possible to resolve the eddy is 2x2 cells, or consist of 4 cells for 2-dimensional. So if we have the eddy this diameter with the diameter of 2 blocks or two mesh, it will be resolved. But if the eddy is smaller than this, let's say this small or this small or this one, it will be not resolved or unresolved. Then in large eddy simulation, we also introduce some modeling called the subgrid model. So this value or this size is called the subgrid because it is below the size of the grid. So we have various subgrid models in the OpenFOAM, like a small Gorinsky and anything like that. So the basic idea or the basic the basic idea is basically we have to make the mesh more than 4 cells to capture the or to resolve the eddy itself. But by just making this small mesh or this 4x4 to capture the eddy, we will not capture the whole energy cascade like this. Let's say if we are resolving this large with this small mesh, it will be maybe covering like 80% or 90% of this energy cascade. But if we just resolving this, maybe we just make resolving like a half or maybe 1/3 of the energy kinetic density, which means that we are not capturing the feature of the kinetic energy. So the best practice suggested by some engineers or maybe some OpenFOAM users or CAD user is by resolving at least 80% of the turbulent kinetic energy. It is around here. So the mesh will be the size, around this size, which corresponds to the 5x5 mesh, or 5x5 cells. But again, this is just only estimation, so you must always validate and check your result after you are calculating this, because like everywhere in the field you will get a different result of the number of or the diameter of the eddy. But the question is how to calculate this or to estimate this diameter of the eddy. We can use a simple estimation by using this integral length scale, which defined here. The L0 or the diameter of it is basically not a single diameter of an eddy, but it is like average value of the eddy diameter in that location. So we can estimate it using kappa or the turbulent kinetic energy and the epsilon, which the next question is where we can get these values, and the answer is you must run it from the runs. So the best practice to run this large eddy simulation is by first running the RAS calculation to estimate the value of the kappa, epsilon and omega, so you can calculate or estimate the integral length scale. After you get this integral length scale, you must or you should estimate that this value is larger than these 5 cells. So sometimes we must define or we can define the integral length scale divided by 5. Then you can plot it on the paraview. So if the value is following this number, it will be fine for your mesh, or you must reduce your size of the mesh. And these are the large eddy simulation family provided in the OpenFOAM. We have a small Gorinsky, Chi Epsilon, dynamic, Wally. This is also well known. But maybe if you are interested in the turbulent modeling or the less, it will be a long discussion. Maybe we can make please comment if you want to make that like that series. on this lecture. Maybe I will make that special series for the large AD simulation. But up to this point, at least you get the idea what is the difference of the large AD simulation and the runs in the use of the OpenFOAM. And I will show you the little bit about the RAS, so you can maybe go to the tutorial folder in compressible and pitch the LES. You can check here some of the boundary conditions, which are maybe the velocity that will be slightly different by using the fluctuating inputs, and maybe you have no tilde and new t here because of like the turbulent model that we are solving here is basically the dynamic equation. So some different turbulent model or subgrid model will have like different parameters. And in large AD simulation, we also need to understand the topic of current number, which is maybe not here, but yeah, the current number basically is the ratio of the velocity and the size of the mesh. So, and the like the time step. So if you have smaller time steps and the smaller, like if you have a higher velocity with a smaller mesh, you will need smaller time steps. That's why large AD simulation has a high constraint of the computational effort, because we have to make the delta t or time step as small as possible while maintaining the size of the mesh as small as possible as a consequence of this calculation. So the conclusion of this large AD simulation, you can actually run this simulation if you want to check the feature of it. But the conclusion is, by using the proper way to simulate the large AD simulation, you will need much more computational effort due to its mesh size and also its small time steps. But again, it is worth to learn the large AD simulation because some researchers say that this large AD simulation is the future of the computational fluid dynamics, and you can also make like a better animation by using this large AD simulation instead of using runs. But that's just like it's not that really significant.